Hey everyone, and welcome to The Explainer. I am absolutely thrilled to have you here today because, well, we're going on a truly fascinating journey together. We are going to explore a massive, and I mean massive, breakthrough in scientific computing. We're going to start way up high with some incredibly advanced AI software algorithms, and then we're going to zoom all the way down, literally to the microscopic level, to look at the nanoscale microchips that are making the whole shebang possible. So if you're interested in the absolute bleeding edge of AI hardware, you are definitely in the right place. Let's get into it. Here's a quick look at our agenda for today. First, we'll tackle the AI hardware problem. Second, MLPs versus emerging CANs. Third, simplifying complex math. Fourth, CIM architecture. Fifth, the memristor secret sauce. And finally, we'll wrap up with revolutionary speed and efficiency. All right, Section 1, the AI hardware problem. Deep learning is hitting an energy wall. Okay, let's dive into this by first understanding the massive roadblock that's currently facing the entire tech world. As our AI models scale up to handle more and more advanced problems, their energy demands are absolutely skyrocketing. And the underlying issue here is that our traditional general-purpose chips, your standard GPUs and CPUs, they rely on constantly moving data back and forth between memory and processing units. These constant, super power-hungry data transfers create a massive bottleneck. If we want to achieve extreme scaling for complex scientific computing, relying on standard chips is simply unsustainable. We're literally hitting a wall. Which brings us to Section 2, MLPs versus emerging CANs, a massive shift in software. To really understand this shift, we need to compare the old with the new. For years, multilayer perceptrons, or MLPs, have been the backbone of deep learning. MLPs rely on linear weights and massive matrix multiplications. Think of it like brute force heavy lifting. But now, we have Kolmogorov Arnold networks, or CANs for short. Instead of linear weights, CANs train nonlinear activation functions. It's kind of like switching from brute force to, well, custom craftsmanship. Because of this clever switch, for certain scientific tasks, CANs can actually match MLP accuracy while shrinking the model size by up to 100 times. That is a huge deal. But, there's always a catch, right? And the catch here is latency. Standard GPUs are highly optimized for the linear math used by MLPs, but they are honestly terrible at computing the complex nonlinear functions that CANs require. Running a CAN on a standard GPU can exhibit anywhere from 5 to 100 times higher latency. So we've got this incredibly efficient software model that our current hardware just fundamentally cannot process efficiently. Section 3. Simplifying complex nonlinear math. The algorithmic solution. So what does this all mean? How do we actually fix this math problem and make these complex equations easy for a machine to digest? Well, to solve this, researchers use a brilliant strategy called piecewise linear, or PWL, approximation. Instead of forcing a computer to calculate a wild, messy, continuous curve all at once, the algorithm just chops that complex curve up into predictable, bite-sized linear segments. Let's walk through exactly how this little trick works. Step 1. The complex function is divided into linear segments, each with its own slope and intercept. Step 2. When an input comes in, the system simply identifies which segment that input falls into. Step 3. It computes a very basic multiply-accumulate, or MAC, operation. This is absolutely genius because it guarantees that no matter how complex the original nonlinear function was, it's always going to take the exact same predictable amount of time and energy to solve. All right, Section 4, Compute in Memory Hardware Architecture. Computing data where it lives. Let's look at the physical architecture itself, the compact floor plan of the 16-core K-SIM chip. K-SIM stands for Kolmogorov Arnold Compute in Memory. Now remember that massive energy wall caused by constantly moving data around? Compute in memory literally eliminates it by processing the data directly inside the memory arrays where it already lives. Using a highly specialized single-row read scheme, it fetches the slope and intercept for our linear segments in a single, hyper-efficient operation. And this architectural choice drastically impacts the energy footprint. Because the computations are happening locally, entirely within the tile, the chip completely slashes those massive data movement penalties that totally cripple traditional GPUs. This read-centric design is incredibly efficient, but its true power comes from what is physically inside those memory arrays. Moving to Section 5, memristors, the secret sauce. Zooming into the microscopic level. Okay, we're zooming way into the nanoscale now. This is a memristor cross-junction, and its physical footprint is just 100 by 100 nanometers. I mean, that is unimaginably small. These act as microscopic non-volatile memory switches. They're the physical foundation of the entire accelerator, capable of holding the parameters for our math functions with just incredible stability. But having tiny switches is only half the battle, right? You need to be able to read their state quickly without wasting power. Through a remarkably fast RC discharge sensing circuit, the engineers completely avoided using clunky, energy-draining converters. The memristor rapidly discharges a simple capacitor based on its state, triggering an inverter circuit to read the data in roughly 1.5 nanoseconds. 1.5 nanoseconds. It is blazingly fast and uses virtually zero power. Finally, Section 6. Revolutionary speed and efficiency. The payoff. So, we've gone from the high-level algorithm all the way down to a 100-nanometer switch. What actually happens when you combine all of this crazy cross-layer engineering? Well, when benchmarked for computing these complex equations, the K-SIM architecture achieved a staggering 1,996 times improvement in the energy delay product compared to a conventional CPU. Let me just repeat that for a second. Nearly a 2,000-fold improvement in combined speed and energy efficiency. It is mind-blowing. It also vastly outperforms other custom processing units designed for similar tasks. And if you want to look at the raw energy consumption, the system requires just 8.69 picojoules to evaluate a single CAN function. Now, to put that into perspective, a picojoule is 1/trillionth of a joule. This insanely low footprint means we can run highly complex AI models on the edge, on battery-powered devices without even breaking a sweat. But of course, efficiency means absolutely nothing if the math is wrong. So let's see how this resilience translates to real-world applications. When simulating the notoriously complex Hodgkin-Huxley neuron model, the K-SIM hardware aligns perfectly with the baseline. Despite all those approximations and microscopic tricks we talked about, the math is flawless and the simulation never diverges or crashes. It just works. And this brings us to a completely unique feature of this chip. Because of exactly how it computes functions using those simple memory arrays, K-SIM can natively calculate complex mathematical derivatives on the fly simultaneously with the main function output. Prior hardware accelerators just couldn't handle this efficiently, but K-SIM processes both the function and its derivative in just 43 nanoseconds. So let's summarize this remarkable piece of engineering. K-SIM flawlessly handles wide data ranges, it completely avoids output divergence in tricky dynamic systems, computes math derivatives natively on the fly, and delivers perfectly predictable ultra-low latency. Because of this end-to-end optimization, it represents a massive leap forward and is an absolutely ideal architecture for real-time scientific edge computing. Which brings us to the ultimate question for today. We've seen how bridging the gap from brilliant algorithms down to nanoscale memristors has essentially shattered the AI energy wall for CAN models. So if we can now simulate complex physical models and dynamic equations in real time at the extreme edge using virtually zero power, what impossible scientific problems will AI solve next? Thank you so much for joining me on this explainer, and keep your eyes on the horizon.